If futuristic sci-fi games have one rule, it's that you need holographic, glowing stuff with lots of hexagons all over it. That's how a lot of games do things like shields, and in this tutorial, I'll be showing you how to recreate this effect in ShaderGraph. I'm using URP, but it should work in HDRP and built-in too. Case in point, I'm not sure if everyone knows that you can use ShaderGraph in the built-in render pipeline now, so there's that. The graph and all associated assets are on GitHub, and I'll throw in a bonus VFX effects too. Let's take a look at the completed effect and break down each part of it. It's more complicated than it may first appear. First off, there's the tiled hexagon pattern. Not only does it provide texture, but you may also notice that hexagons are raised very slightly, so I'm also using them as a height map, which prevents the surface looking so flat. Next, there's a glow around the edge of the shield, which helps emphasize the boundaries of the shield and contrasts it with other environmental details. That's a nice touch, but it gets way more interesting when you move the shield through the floor, since that edge now appears at the intersection. It's an entirely separate part of the shader that's doing that. There's a bit of ambient glow on the surface of the shield to stop it from looking so static. On top of that, there's a very prominent scrolling scanline which draws the eye and makes it seem like the hologram is refreshing over time. Sort of like an old school CRT display if you've ever seen the electron gun operating in slow motion. For more fine-tuned details, there are some less prominent, far thinner and more plentiful, slower scanlines also scrolling down the shield. As a cherry on top, if we head into play mode and click the shield, a ripple will radiate from the impact point, along with a VFX effect. I'll only briefly talk about the scripting that drives this effect, and I won't cover the VFX in this tutorial, but it's in the GitHub repo, and maybe I'll make a video on it if there's enough demand. For this shader, I'll include keywords for each part of the effect in case you ever need to turn off any of the features, if you don't like them or need a less expensive effect. There will be quite a few keywords, so it's probably worth noting that Unity has a limit on the number of shader variants that can be generated for any given shader. If you run into errors, ShaderGraph will warn you at the top of the properties list, and you can go into Preferences ShaderGraph to increase the limit, or you can just remove some of the keywords. Let's jump into ShaderGraph now and see how I made this shader. First off, head to the graph settings and make sure you're using a lit shader with a transparent surface. You'll probably also want to turn on rendering for both faces, although that depends on how you'll be using the shield in your game. The other default settings are probably fine, but here are all of mine if you want to check. Now I'll be going over each bit of functionality one by one, starting with basic colors and PBR settings. For the properties, I've neatly segmented everything using categories, which has the nice side effect of also providing nice headings and collapsible sections on any material using this shader. Very organized. I'm using a base color which also provides the alpha, transparency value for the shield. The emission color is probably going to be more noticeable as it controls the color of all the glowing bits of the shield, which is most of it. It acts as the global multiplier for all the emissive bits that we'll be calculating throughout the tutorial, so we'll come back to this later. I decided to just use floats for the metallic and smoothness, but you could replace these with textures if you want. The next thing I added was the glowing edge, which also marks the beginning of using keywords in the graph. Each one is a boolean keyword, and for all of them, I use the shader feature setting, which kind of means what it sounds like since I'm using it to toggle shader functionality, and I set the scope to local so I can tweak it per material. The first keyword is called useEdgeGlow. I also have two other properties. EdgeGlow Strength is a float between 0 and 1, and I hope the name is descriptive enough, and EdgeGlow Thickness is a vector 2, describing the size of the glowing portion as a proportion of the total UV space in the X and Y directions. So if I gave it the value 0.2, 0.1, The glow takes up 10% of the total height of the shield at the top and 10% of the total height at the bottom, and then 20% on the left and 20% on the right. I could have used a singular float, but I didn't, and here's why. The actual shape of the mesh is rectangular. It's about twice as wide as it is tall, which means the UVs look like this. Any texture applied without scaling would look squashed. We'll worry about texturing later, but this also has an impact on the edge glow, because I'm going to be using the UVs to determine where the edges get drawn. To get around that, I'm using two thickness values which will act as thresholds, horizontal and vertical. I could have opted to make the UVs look something like this, which would let me use a single edge threshold value, but then I'd have a similar problem where I'd need to keep an extra property to keep track of where to apply the threshold. Back on the graph, let's apply the threshold. It looks like a large group of nodes, but a lot of these are just basic maths operations. This is probably one of shader graph's biggest weaknesses, since it tends to make some problems look far more complicated than they are. This branch of nodes is taking the UVs, then recentering 0, 0 to 0.5, 0.5 with a wraparound, because it makes the actual threshold a step easier. Horizontally, I'll take the distance from 0.5 and 1 minus the result, giving us a measure of how far a pixel is from the left or right hand edges. If I hadn't adjusted the UVs by 0.5, then I would have to calculate this distance from the left and right hand edges separately, so this is saving a bit of work and making the graph cleaner. Then I use smooth step with the X threshold value to produce an edge with a bit of fall off. Then I do all of that again vertically and add the two results. Finally, I multiply by the edge glow strength and use the edge glow keyword so that this functionality can be turned off at will. This won't do anything yet as we haven't incorporated it into the emission output, but I'll be dealing with all of that at the end. If we did hook everything up, then the shield would look like this. Next, I added intersections with other objects. One caveat is that these intersections will only work with opaque objects. I added two float properties, intersection strength and intersection thickness, which are similar to the properties I used for the edge glow. To work out if a pixel on the shield is on or near an intersection, I calculate the depth of that pixel of the shield using a screen position node in raw mode, taking the fourth component. It's a bit complicated to explain exactly where that value comes from, so you'll have to trust me when I say that's the depth of the shield pixel. Then I subtract it from the depth value that was previously written into the depth texture for that pixel, which is actually the depth of whatever opaque object was drawn here, if any. I use a scene depth node for that. The result is the distance between the shield depth and the previous opaque depth, and if that distance is very small, then this is an intersection. I use the smooth step node once more to provide a falloff, although this time I need to 1 minus the result because this distance is backwards. Then we can multiply by intersection strength and use the use intersection keyword to finish off this node group. Here's what the shield looks like when you move it through the floor. It works if you rotate the shield too, although it's worth noting you won't see the intersection if you angle the camera just right. I think the edges are glowing enough now, so let's move on to some collision ripples. This time the properties are the ripple's origin point, the thickness, the speed, the time since the ripple started, and an aspect ratio, which only needs to be here because my UV setup is a bit abnormal, as I'd explained before. It's worth noting that the ripple origin and time properties will be sent to the shader via a C# script. On the graph, I start by calculating a distance between the current UV coordinate and the ripple origin, taking that aspect ratio into account. If you imagine the preview on the distance node being squashed vertically, it would look circular. To get a singular thick ripple, I provide two thresholds. The lower threshold increases over time based on speed, and it controls the distance of the inner part of the ripple. A smooth step node provides some falloff for the ripple. Actually, the size of that falloff is also equal to the ripple thickness property. Then I add the thickness to the first threshold and do a second threshold with a second smooth step in a very similar way. That second threshold is backwards, so I will minus it and multiply the two results together to get a lovely circular ripple. Well, it's an oblong in this preview, but remember, my shield has special UVs, so it gets squashed correctly. The use collision ripples keyword can turn the ripples off if we want. I won't go into detail about the scripts I'm using to send the ripple origin and time values, but I do want to highlight one thing I didn't know about. When you do a raycast, the raycast hit data can give you information about the texture coordinate of the point you hit if the object has a mesh collider attached. Specifically a mesh collider, no other collider type works. I expected I'd need to do some weird, horrible maths to get this working by myself, but nope. The ripples are nice, but the surface of the shield is otherwise bare at the moment, so we'll add some texturing. The main texture will be made up of hexagons, but first I want to add ambient glow to the main surface which fades in and out of brightness. I'll do it by scrolling noise values down the shield over time. The properties are the glow strength, for which I'll set a minimum and maximum value, a noise scale, and a speed value, plus the use hexagon glow keyword. I'll start by multiplying a time node by the glow speed, then add the white component of the UVs and feed the result into a simple noise node which uses the glow noise scale property. The output is a value between 0 and 1, which I'll remap to the glow strength min and max values. If I turn off use hexagon glow, then we'll just use the glow strength max value for the whole shield. Next we can incorporate the hexagon pattern, which we'll do in two places. We'll have two extra properties, the hexagon texture and a Heightmap strength float. For the main texturing, add the output of the glow nodes that we just added to the output from the collision ripple nodes. We want these two portions of code to go dark at the bits between the hexagons. I'll clamp the result so that it isn't above 1 using a saturate node, then sample the hexagon texture and multiply the texture and the saturate output. On the preview, none of the bits between the hexagons should be glowing. The second way we'll incorporate the hexagon pattern is by manipulating the normals to make it appear as if the hexagons are protruding from the surface slightly. Right at the end of the graph, sample the hexagon texture once more and feed the result into a normal from height node using Heightmap strength, which gives us a funky looking mostly blue preview. Pass the result into the normal tangent space output of the graph and the hexagons should look a tiny bit more 3D than they otherwise would. All that's left to add are the scanlines. First, let's deal with the singular large glowing scanline. I'll need the strength, thickness, and speed properties for this, plus the use big scanline boolean keyword. I'll start by multiplying time by big scanline speed, then modulo the result by 1. This gives us a value that ticks up from 0 to 1, then wraps back round to 0 again. It actually needs to count in the opposite direction, so I'll 1 minus it. The reason I didn't just make the speed negative is because values below 0 break the modulo node. These values go from 0 to 1, which is fine, but I'm going to introduce a small undershoot and overshoot because otherwise, the bottom edge of the scanline would graze the bottom of the shield, then immediately pop back to the top, which doesn't look very smooth. To do that, I'll remap the values to run from minus the thickness to 1 plus the thickness. I'll take the distance between that remap and the Y components of the UVs, use a smooth step to create a single scanline with smoothed edges, then 1 minus the result because the result is backwards. I'll wrap things up by multiplying the big scanline strength and incorporating the use big scanline keyword the same way I've been doing with most of these features. Now our shield has some very obvious movement going on, which should help to break the monotony a bit. That just leaves the smaller scanlines. These ones are very straightforward. I'll need 4 properties, the scanline strength, texture and velocity values, plus a use scanlines keyword. I'll multiply the scroll velocity by the time and add the result to the UVs. Then, using the resulting new UVs to sample the scanline texture. I'll round things off by multiplying the scanline strength and incorporate the use scanlines keyword, which you ought to be used to by now. Now we just need to pull everything together, which is thankfully mostly a series of additions. I'll add the edge glow nodes, the hexagon pattern nodes, the small scanline nodes, the object intersection nodes and the big scanline nodes together multiply the result by the emission color property that I mentioned near the start, and output the whole thing to the graph's emission output. If everything was connected properly, you should be seeing a glowing shield just like mine when you create a material and attach it to an object. Thank you to my Patreon supporters for making this video possible. Love you all. If you like my work, then there are lots of ways to support me in the video description. And if you're looking for a video a bit like this one, check out some of my older work on holograms. Unity has changed a fair bit since then, but I think the information is still valuable. Thanks for watching, and I'll see you in the next tutorial.